he directs their Statistics and Data Science Center and is part of Laboratory for Information and Decision Sciences LIDS at MIT. His research focuses on statistical inference and stochastic networks. In the last few years, he's been working on matrix completion methods, and we'll hear some of that today. Um, Devavrat received his bachelor's degree from IIT Bombay. Very illustrious batch, where top researchers came during that batch, and Devavrat was the President Gold Medalist in that illustrious batch. He won the George Danzig Best Dissertation Award in his PhD thesis, and he got later the Erlang Prize through the Applied Probability Society, which is a very prestigious biannual prize, um, and many, many other recognitions. So we are very happy to have him today. Thank you, Devavrat, for getting up this early in the morning, making time for us. Looking forward to your talk.
Well, thank you. Thank you for having me. And my sincere apologies for not making there in person. However, I look forward to being on campus in person, hopefully in soon near future. Appreciate the opportunity to speak with all of you. In this talk, I'm going to primarily discuss the topic of matrix completion. Stated simply, if you have a simple spreadsheet with numbers, some of the numbers are missing, some of the numbers are noisy observations, and then you want to fill up all the missing values, all the noisy observations, you want to correct them, denoise them. That's the task of matrix completion. At some level, it feels very simple, maybe a bit gimmicky too. Over years, especially since got formulated in the early 90s, it's done some wonderful things. First, it has fueled important intellectual growth in computation, machine learning, statistics, applied probability. So very much cross-disciplinary. On the other hand, for me personally, matrix completion has come up in various somewhat mysterious incarnations in the problems that you would not anticipate them to be there. And really what I want to do in this lecture, this presentation, is it's more of a survey type presentation, where I'll walk you through a personal journey. It's not a survey of the field, so it's personally biased. So my apologies to begin with towards that. And hopefully some of these things, some of you would find interesting and exciting, because there are lots of wonderful intellectual challenges that are there in the topic itself. I presume that some of you, if makes sense, would ask me questions as the talk goes. I can, since the seminar hall here is nicely structured, I can actually see the broader audience, so which makes it really nice and at least a much better virtual experience. So please feel free to stop me, and happy to sort of clarify things in the middle. Okay. So here's the plan for the presentation. I'm going to start with a very simple motivating example. That example will help us formulate sharply the question itself. That will lead us to ask a simple question: what does a generic model make sense? From there, naturally, as we will see the model itself, there are two parts that would emerge. One is how do we model the notion of what entries are observed? And then second one is whether it's you design it or they're given. Okay? And then so we'll talk about in each of the contexts, just in broad strokes, what the question looks like, some of the examples of the methods to solve these problems. Then finally, I will go to the various applications where this naturally comes up and some of the challenges. Throughout, what I will do is I will give a few of the references. Uh, think of these references as pointers. There is just a massive literature out there. And in that sense, you would take my referencing approach more of a Markovian. On the right-hand side are some of the examples and the context where the matrix completion naturally comes up. I may not be able to go and touch upon all of those things, but few of the examples from here that I will pick. Okay. All right. So first, we'll start with a simple motivating example. So consider a setting where we have two players. Imagine that as Sneep and I, we are playing a game of chess. And what you want to do is you want to come up with some sort of ranking scoring, very much the ELO score, for example, that for chess people have. And let's call those scores maybe inherent scores, which nobody may know, but there's an inherent skill. That's a V for one of us, and then W for another one. Okay. Now, of course, we want to estimate that. The thing that we have at hand is when these two players play the game, who wins and with what chance. So a simple model, multinomial logic model, has been around for a long time. What it would say is that, well, when one of the player plays with another player, they win proportionate to their skill. Okay, and put it simply, this is the chance that this person will win. This is the chance that this person will win. Okay. Now, of course, we won't know the chances because we don't know the skills. But what we would know is two players play the game, and then we have the outcomes. So here I'm just showing examples of 8 games. Out of these 8 games, 3 times this individual wins, and then the 5 times this individual wins. Okay. Now, given these outcomes, now I want to figure out what is the estimate of skills. Now, if you believe in this model, it's pretty simple because, at least empirically, we know that this looks like 3/8, and this looks like 5/8. And so from there, we can sort of, and assuming that sort of we have normalized V and W to add up to 1, we can actually solve this equation precisely and get the answer. Okay. In particular, here just I'm putting those things. So nothing unusual, nothing special. Now, imagine that we're trying to do the same thing across many players, and maybe this simple approach may not work. So towards that, let's think of where a little bit complicated version of the same simple approach comes to the same answer, but that will allow us to actually get to many player setting, and especially a setting where, there are lots of players. Maybe Sandeep and I play, maybe Sandeep and somebody else plays there, but I have not played with that somebody else. And so these are not fully connected, let's call it playing network, and we still want to do this type of inference. And this is where maybe this Markov chain view of this might be very useful. And here what I'm suggesting is that let's think of what's known as a reversible Markov chain, where I think of each player as a node in the network or node in the graph. And we're going to design a Markov chain so that the stationary probability or the long term that sort of that this state is where Markov chain lives is proportional to its skill. And one such Markov chain would say that, well, in this two-player setting, you will jump from here to here with skill proportional to the other player. Again, this is a pairwise setting. One can do simple calculation, convinces that indeed the stationary probability in this simply designed Markov chain is exactly proportional to the player's skill. Okay. So again, we got the same answer as before, but in a little bit more complicated manner. It's almost like instead of holding ear like this, we took all our hand and sort of turned it around. But this now starts becoming useful when we start thinking of, again, many player setting, and especially not all players have played with each other. And then one designs the Markov chain where for any player, you go from that player to another player, assuming they have played with each other, with probability proportional to the other player's skills in a relative sense. Turns out that indeed, if the model was true and we had enough observations for each pair of players, and again, not all pairs need to be observed as long as the pairs of players for which we are observing things are connected, then still similar behavior will continue to be true, and we will indeed find the right stationary distribution. Okay, so we went from simple setting to a little bit complicated setting, in particular, naturally a setting where you would have lots of very realistic setting where you have very partial observation. Turns out that one can carefully learn this, and the error of estimation of skill in this setting would scale proportion to how much observations we have per pair of players, and how does the structure of connected network look like. So if, for example, the collection of players who have played with each other and two players are connected by a long path between them, then maybe errors would amplify. Otherwise, errors won't amplify, and that's what captured by effectively this term. So now what does this have to do with matrix completion? Okay, well, this is an example of a following question. In a sense, we have a true underlying matrix where if player I and player J play with each other, then the chances of going from I to J is proportional to the other player's skills relative to the first one. So in a sense, this is the matrix that of my interest. If I know this matrix fully, I'll be able to compute its stationary probability and hence skills. Now, I'm not going to observe this fully. Instead, noisy observation will be there. That is, for maybe a pair of players, I have observed they have played 3 times. And every time they have played, in a sense, it's a coin toss with a bias that's equal to this, or bias that's equal to this. And from there, I want to find out the stationary distribution of P. So noisy observation of P, from which I want to find stationary distribution of P, which is effectively rank 1 approximation of P. Okay, so in a sense, trying to observe, I've got true matrix, noisy observations, not all entries are observed, and I'm trying to learn something about true ground truth underlying matrix. Okay. And as we think about these kind of questions, one natural question comes up is, can we design that? Who should play with whom, how often? Imagine that we're in the university setting, and every year we have to admit students, for example, and students have wonderful applications. And then there is a panel of faculty members who are trying to actually read these application folders, and based on that, they're trying to decide who should be admitted. If there are 100 applications, and then there are 3 faculty members, one option is that all 3 faculty members read all 100 things. Might be too much. If we distribute it, maybe one person is very generous and another person is not. And then we get into this difficult situation where we are potentially admitting a biased sample. So if we think from that perspective, and if we think of any 2 applicants as players in this setting, and then we're getting sort of some kind of a comparison coming out by set of faculty members, and maybe this might be sparse, then that's a very similar setting. Okay. So in a sense, this type of question comes up everywhere. And then the question is that how do we design it? That is, which faculty member gets assigned to which folder is a design choice, or given a design and given assignment, given observation, how do we estimate it? It's an estimation question. And many a times we might have only one observation per entry, and questions can we still say anything about it. So these are the style of questions that would come up. This is a simplest version of this question, and that makes it a question of matrix completion. Now, I've gone with the simple example for last 15 minutes or so. Let me pause here for see if there's any questions, comments.
Hi, I actually had a basic question here. So, how is this formulation different from standard dueling bandit setting?
Um, so, in the context of bandits, right, what you have, at least in, in a simplest setting, um, okay, so dueling, so there are bandits and then there are dueling bandits, right? So I think for
So, I'm
um,
dueling bandits wherein we choose two arms at a particular time and we get a relative feedback as to which one is better and which one is not, and not a subjective feedback.
correct. So I think you could definitely sort of think of 2 bandits, and if you formulate them or outcome as a 0, 1, and then think of their outcome as coming from multinomial logic with this type of setting, then indeed it would be, at least in terms of outcomes, it will be similar. Now the question is that are you actively choosing with the aim of minimizing certain metric, or towards that, then that will sort of become a specific bandit-like formulation. Okay.
But we can also do typical ranking problem in there, right? By that I mean a total ordering kind of stuff, or best.
Abs- Absolutely. So in that sense, if you formulated your dueling bandit problem this way, then indeed it will be a special case of this.
Oh, cool, thanks.
Absolutely. Thank you. Okay.
No, I think there's one more question. Yeah.
Ah, okay. Thank you.
So is this a stochastic matrix, column or
Uh,
row?
so in this specific case, P itself is the way it's defined is a um, transition matrix of a Markov chain. Okay, it is not necessarily stochastic. That is not all the rows and columns sum up to, or rather, um, it doesn't sort of, not all rows and columns sum up to one. Only one of them sums up to one.
The missing entries by the higher order transition probabilities
What do you mean by that?
means A has defeated B and B has defeated C, but A has not played with the C. So the
Perfect.
transition probability from A to C should be the multiplication of the two probabilities A to B and B to C.
Not necessarily true, right? Because the true underlying matrix of interest that's there, okay,
Okay,
is,
thanks.
yeah. Hmm. So I want to sort of take a step back from this question and say, put it in a broader context. And a broader context uh, leads to the following generic question. And the question is that I have a matrix, let's say n by m, and that's a ground truth matrix. I observe noisy partial observations of it. That is, some entries I observe, some entries I don't. When I don't, I call them stars. When we observe them, they're sampled as per a distribution. That distribution has something to do with x. Okay. In particular, in here, I'm trying to encode that on average, the distribution of y is such that on average it's equal to x that I care about. And from these noisy observation of y, I want to estimate x. So I want to estimate x so that x is x hat is close to x, or x hat is close to some a low rank approximation of original x. In the case of our setting, trying to find the rank 1 approximation, more generally, we might want to get the whole matrix, or maybe the whole matrix itself is a low rank, and we're trying to estimate that. Okay, so that is, in a nutshell, the question that we are trying to solve. And again, this has been around in a different form for a very, very long time. In the one context of at least form of econometrics has been around through factor analysis in SWOTs. In the context of, let's say, modern machine learning, it came into natural existence as when people started thinking about recommendation systems. Okay, so now as we start thinking about the model for this question, how do we model it? Here is an approach. It's a matrix. And let's suppose there is rows and we have no information about rows, no information about columns, the way I have formulated the question. That is, row number 27 doesn't mean much, or column number 49 doesn't mean much, it's just a number. So that means that I can permute rows and permute columns. From the perspective of information, nothing has changed, which means that if I have a method, an estimation of method that takes the original data and produces something, or it takes the permuted data and produces something, its efficacy should not change, because information in the row entry, what the row index is or column index, there is nothing. Putting it other way, there is a distributional invariance in the data from the perspective of at least a model or generative view. And if I have an infinite dimensional data, both in terms of number of rows and number of columns, then this is effectively what I would call an exchangeable distribution. That is, we're observing sample from a distribution which is exchangeable, permutation invariant with respect to row and column. And if we take that as a generative hypothesis, then there are natural canonical representation that have been worked out. Again, just the way for one-dimensional, Definity had a beautiful characterization for one-dimensional representation. For two-dimensional representation or higher dimensional representation, there's a very nice work that has emerged over the last 50 years, which in a nutshell would say that the way we should think about the random observations, assuming they're observed, is some measurable function of parameters associated with the row and column, plus some idiosyncratic noise. Okay, so in a generative form, one way to think about it is that for every row, we're going to go and sample some parameter uniformly at random from 0, 1 independently. We'll do the same thing for every column. So now I've got parameters associated with row, parameters associated with column. Then there's one fixed measurable function that applies to every entry that gives me this entry f of theta I rho j. Effectively, that represents xij in our formulation. And then epsilon ij is idiosyncratic noise. Okay, it may have a different distribution per entry, but on average it's 0. And that's how sort of we lead to yij. Now, of course, there are a bunch of complications here, and it is very generic model because f is a measurable function. That makes it very hard. But this is just a certain simplicity and beauty to this. Okay. Now, as we think about this, there's a part which is observation. That is, if I observe an entry ij, what my random observation looks like. And then there is which entry we observe, that is observation pattern. Observation pattern also had a similar thing, that is, it's also a 0-1 matrix. So it also makes sense that it would have a similar model, but maybe different function that drives the outcomes and different, let's call it these row and column features that drive the outcome. So again, this is a model, very complex model. We may or may not be able to do anything about that, but at least it's a representation. And now then sort of one starts thinking about, okay, what sorts of structural assumption makes sense on these? One structural assumption could be that, well, these functions are not generic measurable function. Maybe they are Lipschitz function, continuous function, in which case, the moment we put some such structure assumption, for example, Lipschitz function, which are L2, then there is a natural singular value decomposition for this function that exist. In particular, for these class of functions, one would conclude that effectively they're approximately low rank. Okay, what that means is that a function of two variable can be decomposed as some singular values, so countable terms, um, multiplied by a function of first variable and then the function of a second variable. And number of terms, we can keep it truncate to finitely many because the spectrum is finite. In effect, suggests that for all such functions, we could have a smaller decomposition, which is combined pairwise functions of one variable or another, and that approximates the original thing really well. Once we make these type of assumption, then our model reduces to the following setting, that yes, we have observation, which is mean plus a noise. And the signal is effectively a low rank decomposition in this sense, the functional sense. Similar happens for the observation pattern. It's just that the factors driving observation and factors driving observation pattern are different. Putting it in more generative form, there are collection of latent unobserved factors. They together drive the things that determine observation pattern and the things that determine the observations themselves, in particular here, the signal and then the noise. And then sort of that leads to what we observe or not. Okay. And given such setting, the question is that this observation pattern, it could be designed because, as one of you pointed out, in the context of dueling bandit, maybe you can choose which two arm actually are compared. That's a design approach. Or I'm just given that here are the entries I've observed and go do something with it. So that's one part. And then irrespective of that, depending on the structure of the signal, in this case, approximately low rank, you want algorithm that can recover it. We might have a different goals in terms of what estimation error we are looking for and not. And then the question is that how does this drive different applications? Okay, so those are the type of things I want to talk about next in remaining maybe 20 plus minutes or so. Okay, before I proceed further, let me take again a short pause to see if there are any questions, comments. Okay,
Go ahead, Devavrat.
yeah, all right. So maybe first I'll start with a setting where we can actually design, we can choose which entries are observed or not, and then we'll go to the part where it's given. Okay, so let's start with simplest possible setting. Let's start with simplest possible setting of rank 1 matrix. Um, Forgetting singular values, and maybe I will just absorb them in one of the factors, then ijth entry would look something like ui times vj. U is a row factor, v is a column factor. Okay, and if my matrix is n by m, then there effectively I've got n plus n minus 1 because I can normalize things. The question is that how many observation do I need and how should they be placed? And I have full freedom here. And for a second, let's assume that whenever we observe the entry, it's completely noiseless. That is yij equals to xij, just to keep things simple. So I want to find x. I need to decide which entries to, and I've told you that it's rank 1. I'm going to tell you that whatever you will observe, it will be completely noiseless. And can I sort of recover the matrix? So one approach could be this, simple, is take the first row and take the first column and observe all of the entries out of them. And then because of rank 1 structure, a little bit of calculation would convince you that any entry can be written as product of these two entries divided by this entry. Okay, so as long as this is not 0 or not too ill-conditioned effectively, we can use this simple procedure to estimate all entries. And indeed, the nice thing is we've exactly utilized n plus n minus 1 observation to estimate n plus n minus 1 parameter. So nothing can get better. Okay. Now, of course, this is too made up. It's a simple setting. More generally, what you might have is you're trying to compute rank R approximation. And what you could do is you could choose maybe k columns here and k rows here, and simply do effectively Scher's complement, or putting it other way, you're solving form of a least squares, traditional regression problem, done thoughtfully, or these columns and rows chosen thoughtfully so that your corner matrix is not too bad, then it would lead to a pretty reasonable answer. In particular, even if your rank R approximation has epsilon1 error and your observation is epsilon2 error entry-wise, as long as this corner matrix is reasonably invertible, at least up to, or rth singular value is not too small, you can sort of, this simple procedure would give you a pretty good estimation. Okay, and how do you go about finding these kind of corner, or what conditions? There are some of those conditions that are worked out in this this work, for example. And again, this style of approach has been around and been utilized in many places, but just a simple form gives you very clean answers. But here you have uh, a full freedom. You can choose what to observe. Another design approach could be just choose things at random. Going back to that ranking assignment or rankings example, you might just choose pairs of players to play with each other completely at random as per some intensity P. There's each entry you choose to observe with probability P, independent of everything else. And now the question is that how many entries do you need and what algorithm? Okay. This is also known as missing completely at a random setting. One very simple procedure called singular value thresholding. And there's a nice universal version of it. And this monograph, for example, has a very detailed view of methods like this around spectral method, as they're called. So I'll give you a simple example here. If you've seen this, you know it. If you've not seen it, it's beautiful. So it goes like this, that so this is the matrix we observe. That is, some entries are observed. That lots of them are missing. If you have partially observed matrix and you try to do singular value decomposition of it, it's hard. So what you would do is you would replace the missing values by 0. So now you got this white riddle matrix. So whatever entries you had observed, they're same. The entries you did not observe, you replace them by 0. That's what I'm showing on the right. So now you got a full matrix. For this full matrix, compute its singular value decomposition and then truncate it. That is, keep only top R components and then normalize it by empirical observation intensity. There's what fraction of entries were observed. And there are nice clean ways to choose what the R should be and so on. And surprisingly, this does a pretty good job of at least getting you one robust estimator. It may not be the best, but it's a pretty decent one. Okay. Another such method that's been around, at least empirically, for a very long time is called collaborative filtering. And the idea here is, in a sense, like traditional non-parametric methods like nearest neighbors, is similar here. And it's just in the nearest neighbor traditional setting, you do what one calls finding nearest features. Here you're trying to find nearest features where features are themselves observations. Specifically, let's suppose you want to estimate an entry ij. Let's say there's some entry here that you want to estimate. What we'll go is that based on the observed entries, for a row I, you will find all the closest k rows. And for columns j, you'll find the closest k columns. This will give you, effectively, let's suppose for simplicity, say it turns out, suppose that these k rows are row 1 to up to k, these columns are row 1 to up to k, then it says some square submatrix, which is the nearest submatrix that is to entry ij. And in that submatrix, look at whatever the entries you have observed and take their average or take a processed version of it. And that will be effectively a nice collaborative filtering like algorithm. It's like saying that you want to recommend a movie to me. You find all the people and all the movies that are closest to you and the movies that you want to recommend, and then sort of use that as a way to determine whether you should be recommended or not. Again, there are lots of various incarnations of this method itself, and it does really nice. It has all sorts of very nice guarantees. For these class of setting, across these algorithms, what one finds is that the fraction of entries that one needs to observe when one is sampling needs to scale like effectively the rank that you are trying to estimate, but the number of entries goes down like 1 over n. So in a sense, if this was a square matrix, the minimum number of entries you would need is anyways r times n, and you are effectively getting as close to that as possible. Again, there are a ton of nuances depending on one's interest, error metrics, rates, the assumptions, then the robustness of this and all that. And there's a just remarkable literature out there. Uh, in the context of spectral method, for example, this is a very nice survey that one should look for. Okay. All right. So there will be a set of methods where you had a design choice, and it's two types of design that we discussed. Let me pause here, see if there are questions.
They were just a broad question. Do people use deep learning methods nowadays for matrix completion?
That's a great question. So I think because matrix completion is a very, very sparse problem as itself, in a sense, the availability of data itself for a problem itself is limited. Now, one can ask question, what if I had 1,000 different matrices, right?
Mm-hmm.
And you given me those 1,000 matrices, and now you give me 1,001th matrix, right?
Right.
Can I actually learn first all sorts of models from first 1,000 matrix, so that when you give me 1,001st matrix, I can do some form of quotes and quotes transfer learning from the first 1,000 matrix, right?
Right.
Now, empirically, there are things that people have done from there. However, understanding that from uh, mathematical perspective, I think it will be a great question. And maybe folks in the audience some of them might be interested. And the model here that we're looking at, right, is a nice way to look at what a generative model may look like for these first 1,000 matrix, and then when 1,000 plus first comes around.
Right. Right. Okay.
Yep. Okay. The another question type of setting would be, what if things are not designed but they're observational? That is, they're given. Here's a nice example from what I would call traditional panel data literature. Um, and so, as we know, United Kingdom went through this Brexit where they exited from European Union, and there's a ton of debate before, and then there's been a ton of debate after. And the question is that, has this had an impact on economy? And if so, can we quantify it? Okay. One way to do that in the non-ideal world, or an ideal world, which is not real world, is that let's have United Kingdom, two copies of that, one that goes through Brexit, another that does not go through Brexit. And then we run them parallel to each other and see how their economies compared. Keep the rest of the world same, like traditional randomized control trial, A/B testing. Okay. Of course, this is not feasible. Second is, there's also some form of confounding that's happened here, right? There is some form of a bias. That is, it's a Brexit that happened and not India exit that happened, or France exit that happened, for example, right? So in a sense, it might also depend on the country itself, which decided to leave European Union, and hence the outcome of its economy also depends on that choice that they made a priori. That is, the same characteristics might drive their decision of leaving European Union, which also drives their economic outcome. So as such, these selections themselves are biased, and that could have a deep impact on how we quantify these things. Now, there's a method called synthetic controls that's been around for a long time. And that approach effectively helps us quantify this. And I'll talk about that in a second. And it's a very nice application of matrix completion. But first, let me give you the punchline and then come to that. So this method, what it tries to, here's an example, or rather, here's a case study applying that method to the following data. So on x-axis, I'm showing time in a year. On y-axis is the GDP of the country. In particular, here it's the United Kingdom. And here is effectively the time when the decision of the Brexit was made. And now here is an blue is the actual United Kingdom, how it continued to grow GDP wise. And the red is synthetic United Kingdom that's been created, which says that till that point, of course, they were the same. And after that, it did not go through Brexit, what its economic outcome would be. And when one measures this, effectively, this distance looks similar to this distance. And this distance actually looks like a 2008 uh, uh, economic crisis that we had, okay, or financial crisis we had. So clearly, at least if we trust this, this is a big impact that sort of it has had on the economy. How does this fit into the context of matrix completion? Visually, what I'm showing is what has happened on the left-hand side. That is, there's a time, are columns, rows are countries. Let's say the last row is United Kingdom. This is a time when Brexit happens. And this is the data which corresponds to these countries' GDP. And let's leave this out. That is all of this information in gray, which is observed, which is without having impact of Brexit. And in the purple, we observe no data, and that's what I want to estimate, because I have not observed United Kingdom without Brexit. And that's what we're trying to fill up. From perspective of our model, this is what I would call block pattern, because it's this block that is not observed and everything else is observed. If you think about it, going back, the first design pattern that I was showing is very much like this. It's just this is much fatter in terms of observations. Okay, so it's no surprise that similar approach should work and help you solve these kind of problems. And now this, going back to the modeling approach, says, well, if there are common, so let me say, if these unobserved factors, there is the same common factors that are driving the factors determining this block pattern and the observation, if they are the same, then actually this is causally correct thing to do as well. That is, it's while it's confounded, we can still do the right causal inference, and these methods are doing it correctly. Okay. Block pattern is not the only one. There are many other interesting patterns that naturally emerge into the world of policy design. One is what I would call staircase pattern. So what do I mean by staircase pattern? So imagine that there are different policies that are age-based. For example, in United States, for healthcare support by government goes by one program called Medicare for senior citizens, goes something like this. If you are an individual above certain age, you qualify for this program. If you are an individual below certain age, you do not qualify for that program. Okay. And that age limit is, for example, 65. Now, let's suppose you have collected data historically over years, and now you want to understand, is 65 the best place where this threshold should be put? Should it be 60? Should it be 70? which is the right age. And maybe as the population starts growing older and older, maybe 65 should become 68. Now, can we sort of measure the impact of outcomes, maybe healthcare outcome, maybe financial outcome, maybe others, if we change the 65 to 68? Well, historically, we have never observed 68. So how are we going to estimate that? That again fits this pattern perfectly. And here I'm very quickly giving you caricature. For example, I line up all the historical data I have about individuals, younger people below, older people above. And this effectively says that before I did not have Medicare, after I have Medicare. And that makes sense, right? For let's say year 2000, there were some older people which were on Medicare. Some people who became eligible for Medicare at 2000, some people who were younger became eligible for Medicare in 2001 and so on. This is the same staircase pattern. And again, looking from this lens, we can again estimate the counterfactuals, and then it can lead to evaluation that we were discussing. And okay, is something that sort of I've already sort of discussed. So in the interest of time, I'm going to continue. But in a nutshell, this framework now provides a way to reason, at least from a lens of causal inference, when do these type of methods, at least when do we know these type of methods should work? These type of methods may work beyond this, but at least there's now at least some framework we have to argue about it. Sandeep, I believe I've got maybe 2 more minutes or 3 more minutes.
7 more minutes. But
Okay.
we can leave some time for discussions.
Yeah, absolutely. Maybe I'll flash few applications, won't go through details, and then conclude. Okay. So here is one of my favorite applications is time series. Um, so imagine that I've got 8 observations of time series, and now I want to forecast 9th observation. And in the process, I want to also denoise missing value. If I'm a statistician, I will open up a nice statistical textbook that talks about modeling time series, thinking about harmonic component, thinking about trend component, thinking about stationary component, doing all sorts of hypothesis testing, like Dickey-Fuller for stationary and all that stuff. And then I will do that decomposition, learn it, and then put it into, answer this. Alternatively, we could do something like this. And here I'm giving you an example, and there's a more interesting stuff. But think of this 9 time step I want. I will take the blocks of 3 like this, create a matrix. So first block becomes first column, second block, second column, third block, third column. Now I've got matrix with missing values. Potentially, these are noisy observation of true time series. And I will apply my matrix completion approach. And that, in a nutshell, is the algorithm. When I will do matrix completion, I will fill this missing value as well. Okay, if it was only one missing value, then remember, everything else is observed. This is exactly that block pattern again. Okay. And the reason this type of approach is reasonably robust, and I'll give you one simple example. This is a nice exercise. If I give you any sinusoidal, take any frequency. For this, let's say you're observing, say 16 observations, and now you made 4x4 matrix, for example. So I'm taking t observations, square root of t by square root of t, that is square root of t blocks of square root of t size. That will always be rank 2. And it's true independent of the frequency. Okay. Another application that there's a collection of works and ongoing works for us is actually matrix completion can also be useful to speed up and implement very efficiently both centralized or distributed uh, iterative optimization methods like gradient descent. Okay. Again, in the interest of time, I won't go into the detail, but that is something really interesting. In a nutshell, what you're doing is you're looking at iterates, and for each iterate, you're sort of stacking up the, for example, gradient vector, and that matrix itself is a low rank, so you don't need to compute all gradients. Okay, and then there's a sort of a few collection of works that we have, and more interestingly, actually building a good software library that actually encodes this on top of all existing approaches would be very, very useful. Last but not the least, we have used similar methods for in a recent work where it's utilized to build a simulator for a class of network protocols that leads to better design. And this has been a very long project for us because uh, build a simulator, we produced an outcome recommendations. Then there was a real randomized control trial that happened that actually took those outcomes and then evaluated. Our recommendations were counterintuitive based on historical things. So that real trial was very important. So we had to wait for a year. And after that, thankfully, the methods that the recommendations were here were correct. This is an interesting starting point to do something going forward. Want to talk about at least the details here. I'm a founder of a company where many of the things we do are strongly influenced by things uh, that sort of broadly sort of I spoke about. Also, there have been interesting other sort of applications we've found. For example, something that we've worked with in the world of Alzheimer's. And for me, this is a very interesting project because one of my closest collaborators since my grad school day, Damon Wischik, I then ended up working with Damon Wischik's father, who is who has a company called Taurex Pharmaceutical, and then applying that for personalized treatment effect evaluation. Anyways, I've said a lot. I don't think I have time to say much about what's next, but there are lots of interesting things that needs to be done here. And with that, maybe I'll take a pause here, say thank you, stop sharing my screen so that potentially you can see me bigger on your screen and I can see the whole audience here in a full manner. Thank you.
Yeah, go ahead.
Check. Thank you, Professor, for the talk. I just wanted to ask, when you said like block completion, for example, if we take an example of a series where it is 3, 5, if I were to complete on my own, so I could think it could be like prime number 3, 5, 7, and next one would be 11. Or it could be like odd numbers 3, 5, 7, and 9. So in that
Yes,
scenario, there is a matrix block completion. How do we tackle such things?
good. So I think um, one way to view the time series, right, is that there is a some function, some reasonable function, not a very, not a computationally, let's call it pseudo-random function, but there is a function that has a structure like a Lipschitz function, like a harmonic, like a polynomial, and you're trying to, and then the observations are around this function. That's a noisy version of it with missing values, right? When you have a functional form like that, that's when sort of the time series like literature becomes useful. But if you have things like pseudo-random sequence, um, where coming up with a simple function form is nearly infeasible, of course, time series approach may not work. And the type of things that you were mentioning, for example, these are prime numbers or things like that, it's a pattern that you know as an expert, not necessarily comes from a sort of a, let's call it low complexity function class, in which case it will be very hard, right? I don't know if I answered your question.
Yeah, I got it. Thank you.
Hi, hello, sir. You mentioned that for the Brexit case, right, that matrix completion is the causally correct thing to do. Why is that?
Great. So I think maybe without going to slides, okay. So remember, in the context of the way matrix completion was set up in that setting, was rows were the countries and the columns was the time, right? And I say there are factors associated with countries, the characteristics of countries, characteristic of people, etc., that determines what would be the GDP of the country at that time. And then for time, there'll be factors. Let's say the year it is. There are global effects that are going on that might be determining impact on all the countries. Okay. So together, the factors associated with country and factors associated with the time determine the outcome of the country's GDP. Okay. That's the underlying factor model. Of course, we don't observe these factors. Now, what the matrix completion approach in the block setting is arguing is that if the choice of whether we observe that entry or do not observe that entry is a function of those factors, there is a country factor and the time factor. In that case, one can argue from the lens of causal inference that you are doing the right estimation of the entries that you care about. So that's what I meant by it's a causally correct. And there are few references that I have there that sort of actually goes in detail to explain that.
Okay, thank you.
Thank you.
Yeah.
The same problem. I guess you're assuming that uh, the effect on the GDP is only determined by the countries, by the effects or by the processes going on in the country itself. But given UK is a sufficiently important player, I'm sure because of Brexit, there could be some cause and influence that could be going, flowing through different countries' effects, and from there you get a effect back in UK. But you're still, since you're using the data from the other countries, you're assuming that that thing is not there, right?
Correct. So I think sort of what you're asking a question is that maybe if I may paraphrase, is there some form of interference happening? For example, taking this other example, right? Let's say one is we're trying to figure out what is the impact of mask on some health outcome, right? And let's say it's airborne like COVID, then me wearing mask is not just looking at it in isolation is good enough. I also need to look at whether people in my household are also wearing mask or not, right? So that will be the natural interference. In the way data was handled, some of those interference was taken care of by removing some of the countries, but more generally, how does one go about handling this in systematic manner rather than experts dealing with it? This is an active topic of research that is dealing with network interference in the context of causal inference. There are few manuscripts around that are there. One of them we have on archive and few other things. But this is very much very interesting active area of research. That is interference, especially what people call network interference in causal inference.
Hi, Professor. Such an honor to talk to you because a lot of us have sampled the MicroMasters course. So
Oh,
yeah. So my question is regarding the PhD admissions at IDSS. So beyond like basic criteria that everyone knows, can you share some insider tips like regarding like what do you look at and what are the controllables that we can, if somebody wants to apply, they can still do? Maybe it's a publication or maybe completing the MicroMasters itself.
so I think that's a very tough question. I think you guys being you might be the best thing to best way to do that. But jokes apart, uh, so the IDSS PhD program is very much focused on the intersections, as I may call it, or unions, another way to look at it, where individuals who are interested in uh, statistics, machine learning, on one hand, on the other hand, they might be interested in social sciences or interested in uh, computation or interested in other engineering discipline. So that intersection is where many of the students are interested. I mean, you as a university are fundamentally, I believe, from at least a distance for me, are exactly designed to be that way. And Sandeep, please feel free to correct me if I'm getting it wrong. Uh, and I think in that sense, you do have a very good sort of, let's call it educational profile and a background. Coming to the generic natural processes, right? Having reasonable uh, references can go a long way, because as the world works, and it'll always work, is through sort of the smaller community of folks that who know, unfortunately. So that's sort of another thing to think about. That is, uh, and again, don't try too many things. Try one thing and do one thing well. That usually works the best. At least that's what uh, my actually off the record advice be.
Thank you so much. That's like very counterfactual to all the Reddit advice that pick like fill all the boxes and stuff. So thank you so much.
Yeah, I'll say what is Reddit, but then sort of I'll show my age, right?
Quora Reddit.
No, no, I'm joking. Yes.
Any other
You see,
questions?
I know sorry to interrupt, but I have seen some of the younger people around me who actually, in some sense, partially consume Reddit as a place to get news, and it feels so so counterintuitive and contradictory to me. But
So very quickly, Devrat, so this matrix completion is just a name. It applies to tensor completion as well. Is that right?
that's absolutely correct, and I think those are really interesting hard questions. That's actually where I think lots of exciting things should be done in my mind.
Oh, I see. So that's not an established activity.
So there are lots of interesting computational methods, like variations of alternative least squares that have been there. There's some of the interesting mathematical results there. There is a nice computation statistical trade-offs that are there, but I feel that it's way less mature compared to where the matrix completion is, because of this computational challenge that arises. So I think uh, that is definitely very interesting place to think about. The other place where matrix completion with known factors that are associated with that, doing that is, I mean, there's some framework, there are some natural heuristics, but to the best of my understanding, it's been a question that's been both me and my colleague Alberto, we've been obsessed about, and then taking that in a tensor form, it becomes even interesting and maybe a little harder.
Okay, so there's one more question by Vivek Borkar.
Oh, hey, Vivek.
This is not a question. I just wanted to ask whether there's any kind of survey article or something you have on what you spoke about, which could be a good starting point for students or me for that matter.
Actually, so Alberto, myself, Anish, and Dennis, we've been working on this article with Foundation and Trends, thanks to Garud, actually, um, for a while, and we've been running late. So our hope is that before summer we should complete it.
Okay, any preliminary draft available, or I can wait?
Yeah, but I think for spectral method, it's a beautiful analytic thing that I was mentioning that came out of Jinhua Fan and three other authors out of Princeton. Um, Maybe I can sort of share that.
Okay.
It's a spectral method data analysis. Those are the keywords.
Also in the same series, the foundations.
It is in Foundations and Trends, yes.
Correct.
I'll,
Also,
Mhm.
maybe for the time being, you can just forward these slides to one of us.
Absolutely. Maybe Sandeep, I'll share the PDFs with you.
Thanks.
Yeah, thank you.
Okay, so thank you, Devrat. This was a great note to end the conference. You know, it was impactful, simply presented, comprehensive. So really appreciate that. And let's just have a round of applause for Devrat.
Well, again, thank you for having me, and I appreciate accommodating my remote presentation.
Thank you.
Thank you. I will quit. Bye.
All right, so with this, we are done for today for this conference. Next time. Thank you. How many of you are staying back today?